thank you very much for coming, and apologies for the wait, for the delay. I know the traffic was incredible today, so thank you for your time. So my topic today is vibration serviceability and how walking and dancing in specific affect our structures. So a brief summary of this show. I'm going to take you through a vibration journey. And then I spent like 10 years learning dynamic, working on dynamic. I tried to condense it all in 5 minutes for you. I'll talk about design approaches used for designing different structures, and also I'll talk how to apply these approaches on different structures. I'll skip on bridges because they are very similar to floors. I'll talk about human-induced vibration on floors. I'll talk about my favorite one, which is ground actions on grandstands. And we have some real case studies that we've done in curtains. I'll go through it with you, and then I'll give you a brief guidance on what design documents we can use for this subject. All right, just to give you a flavor of what we will be talking about, I'll start with a couple of videos. So this is the famous Millennium Bridge in London. The first day they opened it, and then the next day they closed it. And you can see some people thinking, oh, it's vibrating. Let's push it more. And let it vibrate more. Some people are being a bit annoyed, they're not very happy about it. And the problem was actually there was not sufficient damping in the structure. You can see that the structure is still safe from ultimate limit state point of view. But it's not very pleasant to be honest. If you walk, you feel yourself like, I'm feeling sick. It's not the best of structures you can try to design. So this is the best example. The second one is a bit more severe. Anyone speaks German here? Look at this structure. It's literally dancing with the crowd. I think it's very loyal to its team as well. That's why I don't go on 10 matches. Well, by the way, this is not Bayern Munich or Borussia Dortmund. This is, a team in the second league. It's called IStructE Frankfurt, and it's mental. All right. So vibration serviceability that I'll be talking about is vibration which is annoying. It's not very pleasant. You don't feel, comfortable in this type of serviceability when your structure is vibrating. Sometimes these type of vibrations affect the existing equipment. So for instance, a client came to us saying that I'm building a lab and we need to check the vibration of the floor, and the reason being is that he's got some calibration equipment, and this calibration, if there is a lot of vibration which is at high level, that it malfunction, and they are very expensive equipment. And sometimes, generally the vibration, when talking vibration serviceability, it's not the type of load case that would affect the structure to the limit state, but you've seen it now. Sometimes it does, and I'll go through an example that we've done, and we have to check the ultimate state for this type of vibrations. All right. So this is my quick guidance to dynamics in 5 minutes. So, according to Einstein, everything is dynamic. Dynamic means everything is moving. So we are dynamic objects. We are not static objects. Even these tables are supposed to be dynamic objects and relative to us. But in the context of structural engineering, it's relating forces to motion. And the way we do it is that, we are engineers. Everything, we study like 5, 6 years, and then the only thing we do, sigma x is 0, sigma y is 0, sigma m is 0. And it's exactly the same in dynamics. But now the forces are a bit different. This term here, we all know it. Stiffness multiplied by displacements or deformations equal to forces. Now we have additional terms for dynamics, and they are inertial forces and damping forces. So what are inertial forces? So suppose you are driving on M6 maybe, or M60, because M6 is always congested. So if you drive at 70 miles per hour, or if you are like me, you drive at 77 miles per hour, but you would like to take advantage of 10%, and then someone just passes in front of you, and you put your foot on the pedal, the brake pedal, very strongly, and what you feel? You're like, you're pushing yourself, towards the car. But this is not exactly what the car is doing. The car is slowing down when you brake, and yourself is resisting this, your body is resisting this motion. That's why you go towards the front, you don't go backward. So this is inertial forces, because your body is resisting this type of change in motion. Damping is an example of when you have a swing. So suppose you're pushing your son, your daughter, your friend, or whoever you're pushing, and you push it the first time, it goes like full amplitude, and if it doesn't go back, it will go back, and then if you don't push it the next time, it will decay, the oscillation will decay, and then it will stop. So this is damping. So damping is the internal force that caused the oscillation to decay and then to die out. And the last term is stiffness. We all know about it. I don't have to speak about it. But the sum of all these forces should be equal to the external force. And all dynamic books, all textbooks, Benzene, Chobra, everyone, they're just talking about how to solve this equation. That's it. If you have the damping is 0 and the external force is 0, you have something called free vibration. And then the purpose of this type of analysis is what's called modal analysis, to find what mode shapes we have of the structure. And mode shapes frequencies are usually given by square root of stiffness divided by mass. Again, if F is 0, it might be damped free vibration, like a swing. You push it the first time, and that's it. Or it might be undamped free vibration. You might have F as harmonic load. F can be any shape, any type. It can be arbitrary load like earthquake. It can be impulsive load like a blast. It can be anything. It can be harmonic, sinusoidal. It can be periodic. Periodic is a sum of sinusoidal loads. And if it's harmonic and has the same frequency of the oscillating body, then we have problem. And that's why you have my sad face here, because this is what we call resonance. A resonance is a very nasty phenomenon, because resonance kills your mass, kills your inertial forces, kills your stiffness forces, and the only thing resisting the force, the excitation, will be the damping. So if you have a damping of about 2%, you'll be expecting a response of about 50% of the input force. That's why if you go to resonance, the design is, you have a failure in design, in dynamic design, and also the structure will go mad. That's why every time we design any structure, the main purpose is to avoid resonance. Is it 5 or 6 minutes? All right. So now I'll speak about what difference we have in the design approaches for vibration serviceability. So starting with the old approach, I'll call it root one approach or root one analysis. And the root one analysis is very simple actually. Just design the structure to avoid any resonance. That's it. Okay, how do we do it? So what we said is that if we have a specific type of structure, we need to achieve some sort of frequency that we are sure it will not be hit by resonance. For floor slabs, we need to achieve 12 Hz. For sports stadia, we have to achieve 6 Hz. And for footbridges, we have to achieve 5 Hz vertically and 1.5 Hz horizontally. So this is how we treat these structures. And this is very easy, to be honest. If you do model analysis, you find your natural frequencies, they are above this limit, job done, that's it. But actually, it's very obsolete, and unless your span to depth ratio is 1:1 maybe, you're not gonna get these frequencies. Unless your structure is very stupidly designed, you're not gonna get these type of frequencies.
Isn't for floor slab isn't generic value?
It is very generic value, to be honest.
In the IStructE manual they have thing 4 Hz for offices.
Well, to be honest,
and 8 for hospitals.
There has been some evidence that this is not quite right. So that's why it's unreliable, it's misleading, and sometimes even if you have frequencies above these limits, your response can cause some high vibration serviceability. So the new approach comes in, and I call it root 2 analysis, and this is actually based on our perception of frequencies of vibration, So we have an excitation, and then how much vibrations we receive is acceptable to us, maybe not. So this is how we decide whether the structure is okay in terms of vibration. Well, this is a complex approach, to be honest. It's not straightforward because you need to do time history analysis, and we need to understand how the structure behaves dynamically. Mostly, we use this approach when this one doesn't work. And trust me, it will not work unless the structure is badly designed. It is accurate in terms of analysis, but the problem we have is that perception of human body is very much based on experience. You are sitting now, maybe comfortable, you've had some pizza, you're okay. So your perception may be very high. So if someone comes up, it's gonna be like, what's going on? But if you are rushing in our incredible traffic, and someone comes and cook you in your or hit and run, baby, you're not gonna feel it because your mood is totally different. You are rushing. You're not thinking about what's going on around you. Or if you are sleeping, the perception gets very high. So it's very much based, on your mood, on your sex, on your, on everything actually. It's been proven that usually females have very high perception of vibrations, and that's why maybe you have very rigorous criteria. Usually it's very much based on experience. So there's nothing like a standard that is acceptable all over the world, saying okay, 5 maybe millimeters per second is acceptable everywhere. So if I talk about what we do for floors, the approach is very simple actually. Start with model analysis of the structure. Have your floor plate model in FE, and then do model analysis, and then check the frequency. If your frequency is less than 10 Hz, then this is a low frequency flow, and probably if you're talking about 4 meter and more, and the design is quite, economical, then you're gonna get a low flow frequency. Sometimes, if you design a span, let's say 2.5 meters, maybe in a corridor, or for any case, and then you have the thickness is about at least 120 for fire rating or whatsoever, you might get some case that the first natural frequency is higher than 10, and this is called high frequency flow. So usually low frequency flows are affected by resonance. So you walk in, and then by your walking you might cause some resonance to the structure. But this type of flows, which is the high frequency flows, it's actually affected by some type of load called impulsive. It's like, that's it. This is impulsive load, and it's very, very fast load, and it's gonna cause the slab to vibrate at high level that we wouldn't accept. So that's why I'm not gonna talk about loads on these frequency or on these slabs, but there's guidance which talks about how we get them. But what we're gonna touch on,
the analysis here just includes like the mass of the slab, isn't it? No loads we have at the moment.
at the moment it's just model analysis.
Just the most, like
Yeah.
the natural frequency of the slab itself.
Yeah, at the moment it's only natural frequency. So we start with the natural frequency, we establish that it's less than 10, then we have to do some sort of time history analysis. So time history analysis means that we need to apply the loads dynamically, and then we apply them when we find the peak mode shape. So this is where we think that the response will be the max. So how much load, what type of load do we apply? We apply actually a periodic load. And you can see from walking, it is a very periodic load. It's not sinusoidal, but periodic load is a sum of sinusoidal loads. So we have the amplitude is given as factor of the weight of the person walking, and in average, the mass or the weight of any person walking is about 700 Newton, about 70 kilograms. It's fair enough. It's all right. Yeah, with diet. Yeah. So the total load actually is the sum of all these, frequencies. So if I'm walking, let's say, at 2 Hertz, then my first harmonic is at 2 Hertz. The second harmonic is at what? 4 Hertz. The third harmonic is 6 Hertz. And the fourth harmonic is 8. Easy. And then, for each harmonic, I get how much load or how much amplitude I can get. And then, this is what I'm showing here. So the first load, the first harmonic, will give me the blue sign, and then the second will give me the green, the red, and then the black. So this is at 3 Hertz, this is at 4.5, and this is at 6 Hertz. Now when you sum them up, this is what you're gonna end up having. This is your time history for walking. This is how walking is applied as a load to the structure. Now this point here is when your foot is leaving the ground. This point here is when your heel is touching the ground, and this point here is when your toes are touching the ground. So see, the difference is like 0.1 second, maybe for 1.5 Hertz. Usually, short people have very high rate of walking, so they walk at about 2.3 to 2.5. Now, tall people usually walk a bit slower, and that's why when you do the analysis, you have to take different ranges from 1.5 to 2.5 in corridors anyway. Okay? Right. So how do we decide whether this is, the vibration is acceptable or not. So as we said, we check the response. And modern codes and guidance say we use something called response factor, R. You're all aware of it. I know in our offices, R is 8, it's too high. R is 10, it's not gonna work. R is 4, it's fine. No, what's R? So R actually is what you get acceleration as R and S. So the mean acceleration divided by 5. Anyone knows by 5? Why by 5? Why not by 10? Why not by 6? Any idea? So 5 actually is the baseline. So if we have a response or if we have vibration of 5 millimeter per square second, no one will feel it. That's why in hospitals you get response of 1. So if you get response factor of 1, that's fine, because you're going to get 5 millimeter per square second. Alright? But as we said, again, this is very much based on experience. There's large margin of terms. You read some document, this is like 1, and then another document says, you can double it actually, that's fine. Another document, you can't double it and take 20% of it. Margin, that's fine. There's nothing very specific. It's not like 1 plus 1 is 2. It's like, this is very stringent, this is okay. So each research body have their own, views about it. So what we assume to do is that we have BS 6472, which is from the British Standards Institute, and say that's fine. Let's go for it and put like a limit for that. Alright, so they said, we're not going to use the response factor now, we're going to use something called vibration dose value. And what does that mean? It's like this horrible equation. God knows what does it mean. It doesn't have any physical meaning. And to be honest, to me, I just got the number and change it to response factor, because I know what response factor is. And some engineers actually use the vibration dose for continuous vibration for tall buildings under wind. And in my view, this is completely wrong. Anyone knows why? Because your perception to vertical loads or vertical vibration is very different from your perception to lateral vibrations. So you can't say we apply the same limit for vibration dose for vertical vibrations and lateral vibrations. You have to adopt the response factor or how much accelerations you get. Anyway, so BSN 66472 1992 said, we're gonna have these values for vibration dose, and let's say during night we have to achieve 0.13 of this formula here. And then we have the grey book, which is from the Concrete Center, and they said, why do we need all this? It's extremely difficult to achieve it. So 0.13, if you translate it into R value, it's about 1.4 sort of, and it's very difficult to achieve actually. And I said, it's very difficult to achieve. We don't need it, so let's take twice of it. And so this BS was revised in 2008, and they relaxed it now. The values here are not the same anymore in 2008. So instead of having 0.13, they said, okay, you can have from 0.1 to 0.2, which is okay. And instead of 0.226, they said you can have between 0.2 to 0.4. So if you use your engineering, mathematical skills and put 0.2 into R value, and you allow for 20%, because this is accepted that if you have 20% margin, this is fine, you end up having R is equal to 2.64. So if you design your flow to have in residential building, if you design your flow to have a response factor of 2.64, it will be okay. Okay, night, day, doesn't matter. But if doesn't work with you, we'll have something else in our back pocket, and this is called the reduction factor or scaling factor. So what is the scaling factor? So actually, well, I said, okay, we're doing the analysis very different from the way that the American code does it. So the American code usually does the analysis like someone is truly walking. You know, we apply the load here, and then the next load is applied here, the next load is applied here, and so on. It's very realistic type of analysis. Now, British codes and documents, they say, no, the way we do it, we select the worst case, and we apply the load like someone's marching actually. But this is not the case, we're not marching, we're walking. And that's why we'll have to reduce, you know, the response we're getting. So because we're not marching at the same point, there's a reduction factor that needs to be applied. And also, even if we have damping, damping doesn't go like up and goes like, you know, it's damping, it's resonance. No, resonance needs some time to build up. So even if you are marching at the same place, you need some time to build up your resonance. So we came up with this R factor, and R factor actually works very well if you have a short span, which makes sense. Because if you have a short span, you're leaving the waist point or the highest mode shape point very quickly, and that's why the reduction factor should be very high. But if you have a 16-meter span, then wherever you're walking, you are always near to the waist or the highest mode shape point, and that's why you're not going to get a lot from this reduction factor. All right? Any question on flows? That's it. Right. I'll move to grandstands. All right. So grandstands is a bit more interesting, to be honest. We have the way we treat grandstands actually is based on how young and lively is the crowd, and it depends also on the type of excitation you can apply. So if you are sitting down, listening to slow music, normally relaxed viewing people, so this is called scenario 1. So we have 4 scenarios, and it's based on excitation. So imagine you are sitting down and listening to Frank Sinatra.
My website is fast. How fast? Turbo fast.
This is very fast. There you go. I can't see any response from you. And this is scenario 1 actually. It's very slow. I tried to find a slower song. I couldn't. I'm not very cultured in music, but Arabic music is also very slow. So there you go. It's very relaxing actually. I mean, I think it's helping the structure more than, you know, applying any load on the structure. Alright? So this is if you're hosting someone who's from the 60s, the 50s maybe, all the crowd is like elderly people. You know, you're not expecting them to come and jump and bob, you know. They're not going to cause any problem to the structure. But the second scenario, okay, audience are seated, but there are some, you know, some people are jumping, some people are doing some noise, okay, but there are not a lot. So maybe we can show this one. Cricket. I don't understand it. I don't know what's going on. I think most of these guys don't know what's going on as well. Like me. But some people are jumping, maybe they understand what's going on. Alright? Is it alright? I don't know. But this is scenario 2. snatch, but not a lot of dynamics. When we talk dynamics, we have to think about periodic things. Someone's jumping is not a dynamic towards a huge grandstand. So they need to be like, whoop, 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 whoop. Something is really periodic, cause some motion to the structure. So this is scenario 2. But scenario 2, once you get scenario 2, you have to think about your dynamics of your grandstand. Now we move on a little bit and say, okay, scenario 3 is potentially excited crowd, and crowd are, really participating in the motion. And I chose this one for it. Maybe not liking mine. Don't like it. I think this is a good song. The crowd they are participating actually. They like it. They're not jumping, they're not very lively crowd, but there is some participation. I like it. So this is scenario 3. Because scenario 3 is a bit marginal, we may not be able to differentiate, to tell the difference between scenario 3 and 4. I said, I'll give you another example maybe. Is this one. Here you go. No salah. Now see the periodic mode now. If Salah scores now, we'll have an earthquake in the grandstand. I'm not going to show the team I'm supporting, by the way, but I support them. Alright? So this is scenario 3. Now we go to the worst scenario, which is scenario 4. And scenario 4 is very excited crowd, standing, bobbing, some are jumping. And maybe this one tells you what I mean by that. Anyone speaks Greek? Very lively crowd. And this is what we need to see. Jumping, very excited guys, they are jumping, it doesn't get any more lively. This is a typical example for scenario 4. And it's very good as well. Now listen. Alright? So these are the scenarios that we could be, finding in any grandstand. So what we do if we have these scenarios? Okay. So the IStructE guidance says, first you do mode analysis, establish your fundamental frequency. Is it less than 6? Oh, sorry. Is it greater than 6? That's fine. You don't have to do anything else. Okay. It is acceptable for all scenarios. That's all right. And the thinking behind it is that when you are bobbing and jumping, you're not gonna excite your structure at resonance if the structure has frequency more than 6 Hz. And then we move. Is it greater than 3.5? So it's very difficult to find a grandstand having frequency higher than 6. So okay, is it greater than 3.5? It is okay then for scenarios 1 and 2, but we've already said that scenario 1 is maybe almost someone is sleeping. Scenario 2, it's not a lot of dynamics going on, but you need to go to root 2 analysis and apply the load to check for scenario 3 and 4. Is it between 3 and 3.5, then it's acceptable for scenario 1, which is not a lot. And then scenarios 2, 3, and 4, you need to do the actual time history analysis. But if it's less than 3 Hz, then you need to do all types. For all scenarios, you need to do your time history analysis. If you have scenario 1 and 2, this is not causing a problem to the ultimate limit state of structure. But if you're having scenario 3 and 4, you have to think about, is the structure able to take this load? And I think we've seen from the second video that the structure was actually about to fall down. It's like, structure was really excited and supporting as well with the fans. So it wasn't the best, the best view you can see as a structural engineer. Maybe for fans, it's all right. Right, so how do we apply the loads for these scenarios on grandstand? It's very similar to walking actually. It's periodic load. So we have this equation, which is sum of sinusoidal loads, again, because we are talking periodic, but they are applied, these sinusoidal loads are multiplied by a factor rho mg. So rho is the effectiveness factor, which means that not all audience are the same age, not all of them can jump at the same time. Maybe if we have elderly people, they will not be able to jump. Not all of them will jump at the same frequency as well. So the analysis said that if you take talking scenario 2 and 3, the worst case is that you run a song at 1.8 Hz. And in this case, rho factor is 1. But if you have scenario 4, the worst case, because the crowd is younger, is very lively, the worst case is to run a song at 2 Hz, and then you get a rho factor of 1 as well. So GI are the generated load factors. So every harmonic is multiplied by a factor, and these factors are given in this table. Now, if you see the loads from different scenarios, you can see here that scenario 4 is producing almost twice the load for scenario 3. It's not something that we can ignore, to be honest. For serviceability and also for ultimate limit state check for your structure. Okay? Now this is a very good paper from IStructE, and obviously these people, their job was to sit down and listen to songs. What a job. And if you read the paper, I think they have listened to about 10,000 different songs from different regions. They were doing Indies, they were doing Hindi, they were doing Arabic, they were doing pop, jazz, almost everything, and they came up with these results. So they said in 60s, all songs in 60s are between 0.6 to 2.6 Hz, and then they've done the same up to 90s, and then 90s said, okay, dance is between 1.3 to 2.8, indie is different, pop is different, rock, we're getting 3.7 Hz. That's very bad. But in average, you see 60s 1.7, 70s 1.8, 80s 1.95, 90s 2. I don't know where we are now. It's getting crazy. I mean, the music is getting so much faster now. And I think the structures are struggling to keep up with us. But also because we are moving, as we said, we are dynamic objects, we're not very static objects. We are adding substantial amount of damping and stiffness in the structure itself. We can't ignore our presence in the structure, and that's why we have to model the structure as the structure and the human, and they have interaction between them. This is called Maxwell model. So my body is modeled as a mass, spring, stiffness, and a dashboard, damping. And then there's also common node between me and the structure. So I'm adding mass, I'm adding stiffness, I'm also adding damping to the structure. The way we calculate it, this is how we calculate the stiffness, based on the scenario, and also based on my natural frequency. And the way we calculate the damping is like a percentage of the critical damping. The critical damping is 2 square root of km. Now m is my weight, or the average weight of any sport fan, which suggests here it's 80 kilogram. You can't remember, for residential it was 70. Now it's 80, which suggests that, you know, sport fans are a bit overweight. I'm 90, by the way. So, all right. So I think we're done with the, you know, how to apply the loads and how we do, you know, analyze it. I'll talk about, you know, some case studies we've done at Curtains. So this is a typical flow from a 36 floor tower in Manchester, and we have to do the analysis of the floor vibration. The layout is very simple. We have like columns around the corridor, and the span is about 6.5, something, if not more. And we have offset core, which is very bad for tall buildings, by the way. But most of the time we are controlled by the architect. We can't do what we love to do. Central core, everything is nice, rectangular and easy. So as we said, we start with the model analysis of the floor slab. And the first mode was suggesting that this is the worst case this is the highest mode shape point. And the frequency was 6.6. So this is what type of flow? Low frequency flow, okay, which might be excited by resonance.
Okay, what mass is included in the first?
I'll talk about the masses. I'll take you through the masses that needed to be included in the model analysis. This is the second mode, which says that, you know, the worst or the highest mode shape is somewhere here. The third mode is for 9.17 Hertz, and it's like half sine wave here, half sine wave here. And the last mode here is saying that this is the highest mode shape point. And it's about 10.5 Hertz. So in 3D, this is how they look. Okay? So what we have to do is to check, you know, the walking, if someone is walking through the corridor, is it affecting people in the apartments? And also we have to check if someone is walking in his apartment, is he affecting someone else? Okay? So the first case was to check walking through the corridor, and the walking range, the walking frequency range is between 1.5 to 2.5 Hertz. And I suspect if you're walking through the corridor, you'll not be walking like very slowly. You'll be walking a bit fast. You know, going to your neighbor saying, "Oh, you need to rush out. You know, we have some problem, or we have the, you know, can I borrow some sugar from you, or anything, you know." But you should be walking very fast. You know, you don't have time to waste in your corridor. But in your flat, maybe you walk a bit slower. So what we had to do is to apply a load step by step because we didn't have any mode shape point here. And it's very difficult actually. So we had to apply the load step by step. So we said, step 1, this is the response we're getting. I'm not going to show you the 40 steps. I'll show you every 5 steps. So 5th step, you see it's a bit moving. Step 10 actually is a very good example because what we said, we have columns, stiff columns around the corridor. And this is very good arrangement because it's confining your response within the corridor. So whenever you're designing a residential building like that, concrete building especially, try to put all your pressure on the architect and say, I want columns around the corridor, I want a stiff corridor, because this would reduce your response. You can't see that. It's more confined now because it is exactly in between the columns. Moving, again, we're getting next to the core walls and almost no response. This is what you want to see. And when we talk concept design, we have to take concept design in dynamics as well. This is the concept design we talk about. The way you distribute your columns. It's not like, I'm gonna get 6 meters, 7 meters. You have to think about all these aspects of loading that you might get, and the way you distribute your columns, the way you put your structure mass makes a lot of difference actually. Right, so the response, as I said, is very confined to the corridor. The maximum response at step 5 and the displacement was about 20 micrometer, about 0.02 millimeter. And the maximum acceleration we were getting was 4.9. If you take this bar by square root to get the RMS, the response factor is 0.7. Great. So this is fine. Now we have to check within the flat. And as I said, we have 3 points having the worst case for the mode shape. So what we said is we have to get some analysis parameters because we apply the loads. Young modulus for concrete is how much usually? Depends on the concrete mix. But we said for vibration, usually you have higher rates of Young modulus. So you go to about 40 gigapascal. That's fine. Mass included in this analysis is the self-weight, finishes, dead load. Everything dead load can be included. Okay? You can take 10% of the imposed load, but you have to prove that it's there. I don't agree with this assumption, but sometimes you need it. So we know that, for concrete relaxes with time. You have some creep, you have some shrinkage. So you have to think about, cracked section properties. Okay, so the moment of inertia is not the same. Usually they crack it by 0.34 or 0.34 for slabs. So what we said, we're not going to crack it for 0.3. We're going to calculate how much exactly it's cracked and taking the SLS moment divided by cracked moment capacity of this slab and check how much it's cracked. But if it says it's not cracked, we're not going to agree with that. We say, okay, it's not cracked, but we're going to crack it by 50%. So a bit conservative, but this is for the peace of mind of the client.
Is the calculation like in Polygram or is it in an Excel sheet?
No, this is
Just manual calculation.
it's our Excel sheet.
Yeah. And how much does it affect when you have the boundary wall and all?
It does make difference, to be honest. If you don't take cladding as support, you'll have about 30% higher response. So because the load itself is very small in walking, you can assume that your cladding actually is supporting the slab, not the way around. Okay? So in vibration analysis, there are some parameters that you need to think about, and you can change it a little bit because the load is very minimal actually, and what you're concerned about is not the ultimate end state, is vibration. So what we've done, we've checked it at 3 points, and we've created time histories for walking at interval of 0.1. So I've created time history for 1.5, 1.6, and so on up to 2. At point 1, this is what we're getting. So this is at 1.5, and you can remember that the frequency of the slab was about 6. So 1.5 was giving me some resonance for the 4th harmonic. So you can see some nice resonance build up here. 1.8 is not actually a multiplication for any harmonic, so no resonance. 2 for the 3rd harmonic, 2 times 3 is 6. So no? There. Okay. So the maximum actually response, we've checked it for 3 different craft properties at 0.3, 0.35, 0.5, and the limit, everything is fine. So this is for the first, mode for the first mode shape for this slab. So everything was okay. Second point, we've done the same analysis, but we're getting a bit higher results at 1.8 and 1.7, and this is for 0.3 and 0.35. But we said we don't have actually to crack it because the SLS moment was about 26.6 and the cracked moment was about 28.3. So it's actually not cracked. I would say we're going to crack it by 50%, and when we cracked it for 50%, this is what we had. The maximum response was about 11.4 millimeters second, which is 2.2 at response factor, and it was alright. And we repeated the same for 0.3 and checked how much cracked section we had, and checked also how much response we're getting at maximum walking of 2 heads. Now remember, if I am checking at 2.1 and 2.5, I would expect this curve here to go something like that. But this is walking in the flat itself. So I am limited to 2 here, which is fine. So you have something to put in your back pocket and check. Okay, it's all right. It's not very scientific, It's based sometimes on your engineering judgment, and you have to satisfy yourself and satisfy your client. You do some analysis and check that it's not very bad, to be honest. So one example, we're doing a concourse for a grandstand, but the concourse is not used actually for watching the match. It's used as a bar. It's used as a meeting, greet and meet area. And this area, we don't expect to see a lot of, you're not bothered if someone is walking around you. It's very congested area. Someone, is eating pizza. Someone is drinking something, So you're not really bothered if someone's walking, beside you. So you say, okay, 8 is fine. Maybe 10 as response factor is fine. So it's actually based on your engineering judgment and to check is it okay or not. Alright, I'll move to a grandstand that we've done. So a client came to us, say, okay, our grandstand actually is not being used in summer, UEFA Champions League is somewhere end of May, we have between June to maybe August, not being used. And we're thinking of hosting some concerts. Is it fine for that? And we said, okay, which concerts are you going to host? And said, okay, someone who we describe as scenario 2 and 3, and someone else who we describe as scenario 4. So what we had to do is to run through the analysis. So we started with the 2D model of the grandstand, and said the first mode actually is this shape, and it is 1.26. It's much less than 6 Hz. But are we really concerned about the roof moving? Can we, as a crowd, can we actually excite this mode? If we are sitting here, you think we can? No, we can't. So this is the first mode, is something that we're not interested in. Okay, move to second mode. Second mode is the whole stand swaying. Okay? Alright, how much frequency do you have? 2.1. It's greater than 1.5. That's fine. We don't have to check this one as well, because the sway motion of the crowd will not create resonance if the frequency is higher than 1.5. Now, third mode was actually vibration of the top racker here. Are we excited if we are sitting? Yeah, of course we can. If we are sitting here and jumping, and someone is playing very exciting music, yeah, we can create this mode shape here. And the frequency here is 3.6, which is less than 6, all right? So we have to think about root 2 analysis, which is time necessary analysis. So we have to check other modes as well, up to 6 Hz. The fourth mode is another shape of the roof deflection. The fifth mode is actually for the second rocker moving as well, which is also less than 6 Hz. I've checked that one, that's pretty stiff. This one, just to give you some idea, this one is about 9 meter cantilever. So it looks small here, but it's about 9 meter. Anyone guesses what UB they've used for the racker here for 9 meter? What would you use? If you were the designer, what would you use? Sorry?
533.
Alright, 533. I mean, you'll have someone is blowing away when you. I think usually you use something like span to depth ratio about 1 to 10 in cantilevers. So you should expect something 933 maybe. If I am the designer, I would go for very heavy plate girder. What they've used is UB686 here, and it is very flexible. And that's why you see this element. This element was added later on because they thought, it's not enough. We'll add something here. Well, this one is not doing a great deal. Okay, the last mode shape here is actually vibration of the second tier here, but this is quite stiff, so it wasn't a problem. So this is me doing some calculations for the dynamic loads we need to apply. So here I'm doing how much load we have to apply. So for, let's say, what's the resonance value here is 3.19, and then what is the growth factor, the effectiveness factor, if you have standard deviation of 0.5 Hz. So all these values are checked. Now also checking how much human structural interaction I need to take into account. Okay? And checking how much stiffness and damping we need to add to structure. And just to put these things in context, if you don't take the human structural interaction into account, you get in about 350 millimeter second, 350 millimeter per square second, which is about 3.5% of G. But if you take it into account, it's about 3% of G. And this is the limit you need to achieve when you're doing scenario 2. So scenario 2, you should not exceed 3% of G. Every row here, because we're doing 2D at the moment, every row is represented by this spring. And the mass, the span between the frames was about 7 meters. So how many seats? We said that every seat is about 0.5 meters. So we had 14 persons sitting between the spans. So this is about, it's like 14 multiplied by 80, which is the weight of any person. Now the results, what we've done, checking for scenario 2, the maximum is 3%. Checking for scenario 3, the maximum is 7%. And then check how much response we're getting from each case. So what we said, okay, we'll apply the full load and check how much response we get. If it exceeds the limit that we are acceptable to or targeting, then we net off one row. So we netted off one row, didn't work. We net off 2 rows. Is that all right? Okay, but we need to check the other scenario as well, because it doesn't work like, you know, okay, what you're singing now, that song, something is scenario 2. You can't move on now. No, it doesn't work like that. You know, you have to take the worst case of the 2 scenarios. So what we said is that you need to net off 2 rows for scenario 3 and 3 rows for scenario 2. You might think, okay, this is not right, but for scenario 2 the limit is much more stringent. We need to achieve 3% only, and here you can achieve 7.5%. That's why the critical case was scenario 2 actually, and we had to net off 3 rows. And then the client said, can we do some more analysis on this one and check, you know, can we get more people to move on? I said, that's fine. What we're gonna do is also check scenario 4. So for scenario 4, what we said, if we take full grandstand occupied, is it okay? You remember, we need to achieve now 20% of G. So for that video, when people were jumping, you know, singing, it's about 20% of G. 20% of G is a decent earthquake, isn't it? So what we need to achieve is 20% of G, but also the dynamic displacement cannot exceed 7 millimeter. So we had to go through the check again and check how many rows we have to net off for scenario 4 for the other concept. And then thinking, okay, but this is scenario 4, we have to check the ultimate limit state as well for the building or for the structure. So what we had to do is to check what is the crowd action when you do the ultimate limit state analysis. And this number is a real number, 0.999 utilization ratio. And I think this is how steel manufacturers do profit actually. And also I had to check the fatigue, thinking about 2 heads motion, and every concert is about 20 minutes. This is how the guidance say, what the guidance says. It's 20 minutes of concert, and then we check the fatigue as well. So fatigue was not a critical case in this analysis. Now we had to do a bit more and develop a very rigorous 3D analysis, 3D model. So you can see here, we've had the roof bracing here, we've added the seats as they are to the grandstand, we've added the concourse and the floors here, thinking about diaphragm, you know. This one took me about a month to develop the model only. And also every person every single person now is modeled as a spring mass dashboard system.
Which
And-
program is that?
This is ETAPS.
8 times.
And everyone, we apply the load on every single person as a dynamic load. And some mode shapes were crowd doing, like Mexican wave. If you have Mexican wave, you have problem with the ground stand. But we had to check, is this correct? So what we had to compare against is the 2D model as well. So remember the first mode was what in 2D? Was roof. And we said we're not interested. Roof again. Is that okay? It's not far off from where we, in the 2D analysis. Still very low, but I'm not interested because we can't excite it. We can't, as a crowd, we can't excite this mode shape. The second one was also the whole thing swaying, and in this case it's just above 1.5, so again we're okay. Third mode, this is where we were interested. It's slightly less than 3, but it is the third racker again, the third tier. Fourth mode, if you remember, the fourth mode was also the roof moving in very odd shape, and this one actually explains what the odd shape was. It was like twisting for the roof. Now you start developing some mode shapes that they don't exist actually in the 2D analysis, like slab deflection or something. And that's why it shows you how important actually to develop for these type of structures, develop 3D analysis, not only 2D analysis, because you have mode shapes that you can't capture in your 2D analysis. And the last mode here is the whole thinking, going mental with the crowd. Okay, but you can't actually excite this mode because the frequency is too high. Right, so we said we need to check, again the same thing for scenario 3, how much displacement and how much acceleration we're getting. Except fully loaded, it doesn't work because it's above 7.5%. But if you let off the first row, that would be fine. Now, in scenario 4, the governing problem was the displacement, the dynamic displacement, because if you are sitting in the second tier and third tier is moving in front of you, you will not feel comfortable actually. So if it's moving more than 7 millimeters, the feeling of the crowd will be that they start feeling panic actually. If you net off 2 rows, you get 7, it's alright maybe. I said we're not going to accept it. So you can see here that there is some value added to the client by developing the 3D model. I'm saying instead of netting off 2 rows here, you need to net off only 1 row, and instead of netting off 5 rows in scenario 4, now you can net off maybe only 2 rows or 3 rows. Okay, but also one of my colleagues went there because we were a bit concerned about the connection capacity, and he climbed with a risk assessment, of course, and checked what the connection arrangement is, and tried to check what the ports are, what the weld is, and then established the capacity of the connection. So this is very ultimate limit state check, and based on the ultimate limit state actually we decided how many rows we need to net off. So in this case the problem was not the serviceability, it was the ultimate limit state.
Excuse me. Can I ask you regarding the connection now? Because some books and technical notes, they suggest that when you model for vibration check, you need to change that from bend, even if it's on site or in reality it's bend connection to rigid connections. Was that the case?
No, this is not the case. It's in modeling. In
Yeah.
modeling, you're right.
Yeah, I mean in modeling, yes.
In
it's
modeling,
not- yeah.
okay. So if the load itself is very small, you take it as rigid. Example is walking. But in this case, the load is not small at all. The load is massive, and you need to actually represent it as it is. So the IStructE
As a
guidance,
pen connection, it's not.
it's
So you-
as
in
a
your model-
semi-rigid connection.
I mean, in your model, have you changed it from pinned connection to semi-rigid?
It's not
or
rigid
rigid?
connection. It's a semi-rigid connection.
In your model.
In the model and in reality.
So you didn't change.
No.
Because it's suggested that, for example, IStructE in one of their technical notes, they recommend that you change that, even if it's on-site pin, you change it because of some. I mean, it's about the friction between.
Okay. So
The
if you have a pin connection, even a pin connection is not pinned in reality.
I
We don't
know.
have. We don't have.
There is kind of semi-rigid there, yes.
So we don't have something pinned, and we don't have something rigid.
Yes.
We have something in between. Okay. So if the capacity of your connection is less than 10% of the plastic moment, this is called pinned. But this is a term. But because when the load is very small, it cannot exceed that 10% of the plastic moment, so you model it as rigid.
Yeah, that's my question.
This is the case. So the case when you model it as rigid and when you model it as it is, depends on how much load do you have. So in walking, for slabs, let's say, yeah, you're right, we have to model it as rigid. Everything needs to be modeled as rigid because the amount of load will not exceed the small moment capacity of the connection. But this load here is quite high,
Yeah.
and it needs to be modeled as it is. If it's pinned and then you model it as rigid, then you are actually not representing the structure as it's behaving. Yeah. So you're right, sometimes
Because in fact, no one mentioning that. In fact,
yes,
it's about they all suggesting that you just model it as rigid, even it's it's bent.
yeah, it depends. It's,
I mean, no one is
it's
mentioning.
correct. It's correct to a limit. It depends
Yes,
on
that
the
limit.
load,
No
yeah.
one is mentioning it.
Yes,
Thank you
it's
so much.
again engineering judgment in this
Yeah.
case. In this case, all right. So this is how we solve this this grandstand. All right. So last thing to talk about. If you are looking for guidance for floor slabs, we have multitude of them. We have P357 from the Steel Construction Institute. We have this grey book from the Concrete Center, and this is actually CSTR 43. It's very, very, very good. I can't stress how much this one's good. Appendix G. You know, everything you need, from theory to application, to everything you need is in that Appendix G. For grandstands, unfortunately, we don't have a lot of guidance, but this one from IStructE is very good as well. And that's it for me. Thank you very much.